Hi, my name is Hanna Komlos. I'm a PhD student at NYU, and today I'm going to talk about our paper, Nearly Optimal List Labeling. This is joint work with Michael Bender, Alex Conway, Martin Farach-Colton, Michal Koucky, Bill Kuszmaul, and Mike Sachs. So in the list labeling problem, we maintain n elements in sorted order in an array of size m, where m, the size of the array, is fixed, and then n changes as elements are inserted or deleted dynamically, subject to the constraint that m is at least some constant multiple of n. So we, as the algorithm, can move elements around in the array, and in fact, we may be forced to move elements in order to maintain the sorted order. For example, here in a second, an element with key m is going to come in. And since there's no space between the elements with keys l and n, the algorithm has to move some stuff around in order to insert this element. And it can choose to move more elements around if it wants to, but the goal is to minimize the cost, which is the number of elements moved per insertion or deletion. List labeling is a fundamental data structural primitive with a long history of study across computer science. The history goes back to 1981, when Itai, Konheim, and Rodek gave a log squared and amortized cost algorithm. And again, the cost is the number of elements that the algorithm moves per operation. This was then de-amortized to a log squared and worst case algorithm by Willard in 1982. And then this was the state of the art on the upper bound side for list labeling for a very long time. And so for this and other reasons, log squared n was conjectured to be the right answer. This is until a couple years ago when, in a paper with many of the same authors as this one, we gave a randomized algorithm for list labeling with log to the 3/2 n expected cost per operation. And then the result that I'm going to talk about today is an even further improvement in this upper bound to O tilde log n. So to give a little more history on this problem, for a lot of the history of list labeling, there was a gap between the upper and lower bounds. So the best known general lower bound is omega log n by Boulinet, Koucky, and Sachs in 2013. And another reason that log squared n was conjectured to be the right answer is that for various natural classes of algorithms, a log squared lower bound was proven matching the upper bound. So for deterministic algorithms, as well as for smooth algorithms, which I'll touch on a little more in a bit. And then when we broke through these with the log to the 3/2 n upper bound, we also proved a lower bound for another natural class of algorithms matching this one called history-independent algorithms, which I'll also touch on in a second. So given all these lower bounds, we know approaching this work that a faster algorithm has to be all of randomized, non-smooth, and history-dependent. And that's exactly what we were able to show. So our algorithm gives log n times log logged n cubed expected cost per operation. And in the rest of this talk, I'm going to talk about how we use these properties of non-smoothness and history dependence in order to get this bound. So first, for some intuition, for any list labeling algorithm, if you have some dense spots in the array and you have an adversarial inserter that can find them, that adversary is able to drive up your cost and make you have a slow algorithm. This is simply because if you have a lot of elements in some region, that's more elements that you're going to have to move in order to accommodate inserts there. So for example, if we had an array that looked like this, where some areas have sparse cost, in fact, most of the areas, but there's a few areas that are dense, so have higher cost, then an adversarial inserter would just target all of their insertions into these dense areas, and these sparse lower cost areas really don't help us at all. So in order to avoid this, smooth algorithms always spread elements evenly, so they select some contiguous subinterval of the array whenever they do a rebuild, and just spread the elements out so that there's an equal number of free spots between any two elements. So this is a good condition to guard against adversarial inserters, but it's relatively expensive to maintain. So as I mentioned, there's a log squared n lower bound. And this is tight because the classical Itai et al. Log squared algorithm also is smooth. So in contrast, history-independent algorithms approach this problem from a different angle by addressing the stipulation of the adversary being able to find these dense areas. So in a history-independent algorithm, the state of the data structure does not depend on the history of insertions. So what this means in our context is that even by being able to control the history of insertions, an adversarial inserter cannot affect the state of the data structure. This means that the adversarial inserter can't create or find dense areas in the algorithm. And so the log squared algorithm creates some dense areas in order to save time and have lower costs for rebuilds, but then an oblivious adversary can't find them and exploit them to drive up the cost. So when we approach this work and think about improving on these bounds, we have to think about ways that an algorithm can use both non-smoothness and dependence on the history in order to achieve better bounds. So before I tell you about how we did that, let me first talk about a general structure that is useful in analyzing all the algorithms that we look at. So this is called a tree of intervals. So we have an array in list labeling, and we think about it in a binary tree. So at the top, at the root, we have the entire array. And then its children are the equally sized left and right half subintervals. And so on all the way down for about log n levels. So we kind of think about the array and all the elements as existing simultaneously on all these levels of the tree. And this is useful because we know the elements are sorted, so at each node, if we specify how many elements go into the left child and how many elements go into the right child, and then we do this recursively all the way down, we've fully specified the array configuration. So this means that we can focus on just determining the left-right balance at a single node of the tree, and this is useful both in how we stipulate our algorithms and how we analyze them. So let's look at some examples of how this would look on the algorithms we've already seen. In a smooth algorithm, because I'm spreading elements out evenly, the same number of elements go into the left child as the right child. And in history-independent list labeling algorithms, although I don't have time to go over in detail how they work in this talk, they choose the left-right balance uniformly at random from a distribution that conforms to some balance constraints. Let's say the two sides can't get too out of balance. And then by choosing this in random, an oblivious adversary is not able to know exactly which state the algorithm is in. Something else to consider is if I somehow had information ahead of time as to which side the inserts were going to go into in the future sequence. So what I would do in that case is say I knew that the right child here was going to get a bunch of inserts. When I rebalanced, I would preemptively move many elements away so that those inserts are going into a sparse location. And this idea was exploited in an interesting way in a paper by Bender et al. In 2007. So obviously we don't get to know the sequence ahead of time, but they consider certain stochastic adversaries on which they are able to predict the left-right distribution of future inserts correctly by looking at the history. And then they leverage that in order to achieve lower cost on such workloads. And that idea is kind of the main inspiration behind the algorithmic tools that we use in our work. So I'm going to go over their paper in a little bit more detail first. So once again, we're going to focus on insertions in one interval of my tree, and I'll use blue to denote insertions that go left and orange to denote insertions that go right. So say I had a workload that we're calling a hammer, meaning it puts all of its insertions in the same place in the array. If I had a balanced strategy that wanted to keep the left and right side with roughly the same amount of elements, then I would move a couple elements away as insertions come in, a couple more insertions come in, I move some more, and so on. And so what you'll notice is that not only do I have to move more elements every time, some of these elements are getting moved multiple times. So if instead I knew that my workload might belong to such a class, what I could do is observe a few inserts first, see that they're going left, and then know that this pattern of inserts is going to continue. And once again, what I would do in that case is preemptively move a bunch of elements away. And now the remaining inserts just get slotted in without having to do any additional moves. So this was a more efficient strategy for this algorithm, as I only had to move my elements once. So in Bender and Who's work, they have certain stochastic workloads. There's hammers, random inserts, and a class called random hammers. And on these, they're able to look at the history and then predict the rest of the workload correctly and bring the cost down to log n. So now we want to take this idea, but apply it to general workloads. So what we have to think about is, whether this is exploitable. So because I'm doing this in a deterministic way, I could have an adversary that looks like this one at the bottom instead, meaning they give me a few inserts that go left, and then I adapt by moving a bunch of elements over to the right. Now this adversarial inserter that knows that I'm going to do this would just target all of these inserts into the dense region that I just created. So now when the remaining inserts go to the right, I have to move many more elements over than I would have had to if I didn't adapt. And then they could just kind of alternate this back and forth, causing me to have a high cost algorithm. So what we want to do is take this idea of adapting to the workload in order to have a lower cost algorithm, but not be exploitable by an adversary. So the approach that we take to this is to build a predictor of future inserts that is just based on the workload's history and works on any workload. And then we use this predictor as well as randomization in order to determine the left-right balance in a way that is not exploitable. And surprisingly, we are able to do this in a way that achieves provable worst-case guarantees on general workloads, even those about which we have no prior information. So to give you a high-level overview of how we do this, our predictions for an interval are based on what we're calling an adaptivity window of some length k, which I'll talk a little bit later about how we choose that. So this is similar to what we saw before. The adaptivity window is the number of inserts over which I observe how many go left and right. So in this example, it's 4, and I observe 3 inserts going to the left. And then having made this observation, I predict that the same pattern will continue for the next window of 4 inserts. And what I do with that prediction is use it to inform my next rebuild. So in particular, I skew the rebuild away from the side that I've predicted is going to get more inserts. So if my prediction is correct, if there are 3 inserts that go into the left side in the next interval, what that means is that I've now set it up that those inserts are going into a lower cost area. So now let's see how this might perform against an inserter that is adversarial. So let's start with the adversarial sequence that we saw for the deterministic adaptive algorithm. So if my adaptivity window, say, had length 4, this is exactly the example we've already seen. I would learn over 4 inserts, and then my prediction is exactly wrong for the next 4 inserts. And then this would continue for the whole pattern. So what's happening here is that this adversary is doing a kind of oscillating hammer where the period of the hammer exactly lines up with my adaptivity window, and that's very bad for us. An adversary could use this to make all of our predictions exactly wrong, and then insertions are going into very dense areas. But now let's look at the same adversary, but different adaptivity windows that I could use. So if I made my adaptivity window twice as long and looked over 8 inserts, then the workload looks balanced over the scale. My prediction would be that for the next period, the insertions are balanced. And this prediction is pretty good. It's correct. And so our insertions are not going into a dense side. They're also not going into a sparse side. So this is kind of neutral for us. But something that's even better is if my adaptivity window were shorter than the period of this hammer. So for example, if it was of length 2, then I'm able to correctly predict the next two inserts going into the left side, and then this would continue again for the entire sequence. So what's happening here is that over a shorter window, the hammer is not oscillating. It looks more like a hammer locally, and it allows us to make good predictions that move elements away from the side that is getting the inserts. And then if I had even shorter periods, the same pattern would emerge. So this is the main idea behind how we construct our algorithm, and we're calling it randomized adaptivity. So what we've seen is that if we had a deterministic adaptive algorithm, it would be relatively easy for an adversary to trick it into making bad decisions. But the question we ask is whether an adversary could trick many different adaptivity windows at different granularities. So in the example we saw, the answer was no. So that adversary kind of only made us make bad decisions in one of the windows. You could ask whether a more clever adversary would be able to do something at different scales. And the surprising and cool answer we give in our paper is no. So we are able to define a probability distribution that mixes these different adaptivity window lengths that no worst case adversary is able to fool in expectation. And this is the key thing that allows us to get this faster O tilde log n algorithm. So this is exactly how our algorithm works at a high level. We choose adaptivity windows according to some probability distribution that is, carefully selected. We learn the left-right imbalance for this many inserts. And then for the next window, we rebalance with a large skew away from the side that is predicted to get more inserts. And this is all set up so that at a single level, this has log n cubed cost per element. And then we have log n levels, so that's where the log n factor comes from. Now, since we have a randomized algorithm, we could have some instances where either the cost is very high or even so high that we're at risk of overflowing. This is something we don't want to happen. So what we do to guard against this is just say if an interval gets too dense above some threshold, we're going to revert to the classical Itai et al. Log squared algorithm, which we know works deterministically. And this has log squared n total cost over all levels. So the main technical thrust of the paper is proving that we don't get into this second failover case too much. So specifically, that intervals only get too dense with probability at most 1 over log n. And there's a lot of technical details that go into both how we set up the distribution and the concentration bounds that we use to prove this lemma. So I would refer you to the paper if you're interested in more details about that. So in conclusion, we have greatly narrowed the remaining gap between the upper and lower bounds for list labeling, and we are now within polylog log n factors of optimal. And a couple interesting things. So one is that our algorithm uses very different techniques from the work that broke through progress on the prior upper bound a couple of years ago. And also, this concept of randomized activity that we introduce is the first instance that we know of where an adaptive algorithm is used to improve the worst case performance against general adversaries. So thank you very much for your attention, and please feel free to reach out to me if you have any questions.